Hello, my name is David Giles of Hightex UK Limited, and this is a presentation on the memory protection unit for the XC23XX family of microcontrollers from Infineon. The presentation is in two sections, part 1 and part 2. This presentation covers part 1, which is the theory element. The memory protection unit on the XC23XX family of microcontrollers from Infineon is quite a flexible peripheral and allows you to select a range of addresses which can be protected under the memory protection scheme. The memory protection scheme allows you to select an address which basically has a lower limit and it has an upper limit. So effectively you can specify a range of memory which is to be protected under the memory protection unit. In this case on the presentation you can see that I have a lower address specified as OX 00000 all the way through to an upper address range of OX00B1FF. And this memory range which we have selected here we can protect for read accesses, write accesses and execute accesses. So if it's an area of SRAM, for example, it may well be that we want to prohibit a section of software from actually accessing that, from reading that particular range of memory. And similarly, it may well be that we will grant permission for the software to read an area of memory, but it doesn't actually have the permission to write to it. And it may not just be SRAM areas that we're looking to protect. It may well be that we want to protect an area of the flash memory, so we prevent unwanted execution from this area of memory. In addition to the read, write and execute permissions, we can also select the level, the protection level for that particular area of memory. We have a choice between level 0, level 1, level 2 and level 3. And the best way to picture this is to think of level 0 as being the operating system level, which has access to all of the system resources, and level 1, level 2 and level 3 are the user application code, which have limited access to the on-chip resources. So for example, the area of special function registers, it may well be that you don't want the user application to have direct access to these. So this means that we have a very flexible system. We can specify a start address, we can specify an end address, we can specify which sections of our code have access to that, and we will divide those up by protection level. So we have protection level 0, which is the operating system which has access to everything, and then we have level 1, 2 and 3, which are the user application levels which have selected access to the system resource. It may well be that level 0 has access to all of the system resources, but we may have a bootloader, for example, which we choose to put into level 1, and level 1 only has access to a certain range of SRAM and a certain range of flash. So that may be how we partition it up. The memory addressing range for the 23XX family of microcontrollers is 24-bit. However, the memory protection unit has a granularity of 256 bytes. The way this works is that we have to think of the lower address as being specified with the bottom byte being set to 0 and the upper byte for the upper address range being set to FF. This then allows us to have 16 bits or the 16 most significant bits of the address protected. And this is because the registers that are provided for the upper address and the lower address are only 16 bits wide. And if we had true 32-bit wide registers, then we could have much greater granularity on the address range to be specified. As there are 16 bits, we take the top 16 bits of the memory address to be protected, and we assume that the lower byte for the lower address is 0, and for the upper address range is FF. Now there are actually 12 address ranges which can be specified. The hardware in the MPU unit allows us to specify 12 completely independent ranges of memory which each have their own read access, write access and execute access permissions, which can be tied in with a level 0 protection range, level 1, level 2 or level 3. We can have intersecting ranges as well. So as shown in this foil, we have two ranges. The first is from 0x00 through to OX1FFFF, and the second one is from OX10000 all the way through to OX2FFFF. And so what you can see is that for the first group that we've had level 0 is the range enabled, so the operating system, for example, has access to this range of memories, but none of the other ranges are allowed access. So a level 1, level 2 or level 3 has no access at all to these, and level 0 only has access for write access. As you can see, it has no permission to read that memory or execute code from that memory location. So the only thing that we are allowed to do for this memory location is for level 0 to be able to write to it. If we have a look at the second block, which we have here, the second memory protection range, we can see that for level 0, which is range enabled, we have access both to read but no access to write. So in the area of memory, which is from OX10000 all the way through to 1XFFFF, we actually have a range overlap. And whatever the most permissive outcome of these two blocks is what's allowed for us. So as you can see here, we would be allowed to read from that overlapping range, and would also be allowed to write from that overlapping range as well. And that's because the overlapping result ranging the most permissive outcome, i.e. if there's a true outcome from that, that's all with all the other outcomes from the other ranges. The protection level is either going to be level 0, level 1, level 2 and level 3, and this is described within the program status word. Bits 5 and bits 10 are used to describe what the current protection level actually is. Bit 10 is actually a shared bit. It's used also within the system to describe the HLDEN bit, the hold enable bit. So this bit is only applicable to the memory protection unit when the whole memory protection unit is enabled, and the most significant bit in the protection mode 0 register is the global enable bit for this register. So when this bit is 1, a write to bit 10 of the program status word is effectively a write to the PL1 bit within the memory protection unit. Similarly, a write to bit 5 is a write to PL0 bit within the memory protection unit. Bit 5 is not shared, but for compatibility with bit 10, the write to PL0 is only allowed when the memory protection unit is globally enabled. Now bits 5 and bits 10 can be directly manipulated as the user has direct access to the program status word. However, this is not particularly desirable, as direct manipulation of the bits causes an automatic change in the protection level. So for example, if bits 5 and bits 10 are actually set to 0, if we was to change bit 10 to a 1, to effectively enable protection level 2. Now, as soon as we've written that 1 to that bit, that protection then becomes enabled, and it may well be that we're executing code, for example, in an area of memory which protection level 2 doesn't allow us to execute code from. Similarly with SRAM areas, it may well be that we're accessing the special function register area, and the program status word is one register within the SFR register. So it may well be that as soon as we alter the program status word, then it may well be that as soon as we've amended the program status word that we don't have access to that SFR area. The trick to modifying the program status word is to use the ret-i instruction, because the ret-i instruction actually updates the PSW word, and I'll be talking a little bit more about that later. Here is an example of how the memory map has been organised for the XC2388E device. This is the part which has onboard iCache, and it also obviously has the memory protection unit. I've drawn out a memory map, which is a very good idea when you're starting to allocate resources to your system, and to have some visual representation of how it is that you want to describe your system. And I have all the key areas in here, including all of the reserved areas which are reserved and aren't to be used or accessed by the microprocessor. So for example, I've got from 0 up to 7 FFF, this is external memory space, and from 800 through to DFF we actually have the data RAM, which is the general purpose SRAM area. We have a couple of other areas as well. We've got the dual port RAM, and for this particular part we also have the cached area as well. So flashbangs 0 through to 4 are mirrored in the flashbank area 8000 80000 to 90FFFF. And obviously, if you're looking at execute permissions, it's important that if you think that you're executing there, say flashbang 1, that if the cache is in operation, that you also provide execute permission for the cache area as well. So in this case, I've tried to set out an arrangement where level 0 has access to all of the chip resource apart from the reserved areas, and level 1, which may be an application level, has some access to the data SRAM area, and it also has some access to the flash area of memory, in this case flashbang 4. Here I've not made it available to the cached area of memory, but it should be in an application where the cache is being used that we make level 1 also available to use that area of cache. This is another example showing the allocation of resources. Here for level 0, I've decided that the data SRAM area is going to be subdivided, and there's going to be an area which is not going to be accessible to level 0. So here there's two blocks of 512 bytes each. So don't forget the granularity of the memory protection unit is 256 bytes. So effectively we have to have sections of 256 bytes. So here there's 512, which is not available to level 0, and similarly the follow-on section. In some of the application examples which I've written, I have a similar memory model to kind of what you see here, where level 0 has access to the majority of the resource, but there's a couple of slices within the data SRAM area which it doesn't have access to. What I've decided is I would have level 1 would have access to this particular area, and level 2 would have access to the area which is below that. And that allows us just to try out a couple of the features of the memory protection unit without having to get too involved with execute permissions from particular areas of the flash. So for this particular example, which you would see here, the ranges for level 0 would be set up as follows. And as you can see, I've written these down from the memory map which I have on the left, and these are what I will be using inside the application to configure the memory map. Okay, so we know what we need to do in terms of organising the protection memory areas, and we have to effectively configure what it is that we actually want via the registers that are available on the device. Now the protection range registers, PRL and PRU for lower and upper, from 0 through to 11, are available indirectly through a protection range address register, or the PRA register. And the PRA register is itself memory mapped to memory location FFC4. The main operating system would effectively configure the memory protection ranges and all of these registers. Because the registers are actually memory mapped, then it is possible to protect these registers from, say, a level 1 or a level 2 or a level 3 application from being overwritten. But what we need to do initially is to load in to these registers the values that we actually want, and the way which you do this is through the PRA register. So for example, if we want to write to PRL 0, what we have to do is we have to put 0 into the right pointer, and the right pointer is the first 5 bits of the PRA register. So we would effectively set all zeros into here, which effectively sets the right pointer to point at PRL0. And then to transfer data into the PRL0 register, we actually have to write data into the PRD register, which is the protection range data register. So a write into this memory location effectively is a write into the protection range registers, which are pointed at by the right pointer. Now this right pointer can be set up for auto incrementing, so some of the bits which I've not detailed here allow you to auto increment on a write. So for example, I could set the pointer up initially to point at 0. I could then write one 16-bit word of data into the protection range register, and the PRL0 is then loaded with the data that has been written, and then this write pointer is automatically indexed by 1. So subsequently a write to the protection range register, a second write, effectively a write now to the second memory location. Now this auto increments all the way through, and it does wrap around. There is a flag which can be examined to determine whether that's actually wrapped round or not. However, as you can see, there are 1, 2, 3, 4, 5 bits here, and the maximum number of registers which we have is 23. So you can't really rely on that wraparound bit, primarily because we only have 12 pairs of registers, 24 memory locations, and obviously the write pointer is 5 bits, which means it wraps around at 32. In addition to a write pointer, what is also provided within the PRA register is a read pointer, and the read pointer operates in exactly the same way as the write pointer. It's a 5-bit memory mapped register, which allows us to access indirectly the range registers. So to read PRL0, for example, I would put bits in all of the registers where I would put bits in all of the read pointer addresses, so bits 8 through to 12 I would set to 0, and then to read it I would read the protection range data register. So a read from the PRD memory location is actually a read from the PRL or the PRU location as pointed to by this read address pointer. And similarly we can have auto incrementing, so I can read all of these memory locations consecutively on the fly just by reading the protection range data register in one go. So that's quite useful. You do need to be a little bit careful that if you have a debug tool and you set up a watch window on the PRD, every time you hit a breakpoint or every time you single step, for example, a read to this memory location is performed, and an accidental auto increment of the read pointer address is actually done. So when you're writing your software, you just need to be a little bit careful that if you're going to inadvertently read this memory location, you could actually be inadvertently incrementing the read pointers on there. In the application example which I've provided, I've made the write pointer address auto increment, but I've made the read pointer address not auto increment. And what I've done is I've just created a little bit of extra software to manage the read pointer in software. So when we write data into the protection range register, the 16 bits of data which are written are actually logged into these memory locations. These numbers represent the high 16 bits of a 24-bit address. So for the low register, for example, we assume that the bottom byte is 00, and for the upper range register we assume that the low byte is FF. What this means is that to have the minimum granularity of 256 bytes, we actually write exactly the same value into both the PRL0 and the PRU0 registers. So having set the ranges up in the PMR registers, we now have to enable the read, write and execute permissions, as well as identify which level of software has access to those particular ranges. This is done through 6 registers, PM0 through to PM5, which correspond to the range registers 0 through to 11. So there are 6 mode registers and there are 12 range registers. So each mode register is responsible for 2 complete ranges. So if you look at the way the bits are enabled, bit 0 of PM0 is special. This is the global protection enable bit, and this is the enable bit, if you like, for the whole of the memory protection unit. It's not duplicated in PM1 through to PM5. In those registers it's actually 0. So that bit is special for PM0. The other bits, we have bits 1 through to bit 7. These correspond to protection range 0, and bits 9 through to bits 15 correspond to protection range 1. And if you look at the way the bits are organized, we have an execute enable bit, we have a read enable bit, and we have a write enable bit. So these are the access permissions, and also we have, to supplement them, the protection level enable bits. So if we want level 0, for example, to be enabled for a given range, we would put a 1 in here, and if we want level 1 to be able to read, write and execute, and then we have to put 1s to each of these bits as well. Okay, to set up the memory protection unit, therefore, you have to set all the ranges up, and you have to set up the protection mode register. This has all the read and write permissions for the different levels. Think of level 0 as being the privilege mode, and the only one able to change these permissions. So that's the philosophy which you kind of need to adopt within your memory protection unit. Once it's all configured, we can then enable the Pro 10 bit, which is in PM0 register, and it's bit 0. If you need to dynamically change the MPU ranges or the permissions, then they should only be done at level 0. So access to the SFR registers should therefore be initially allowed for level 0, because obviously these registers are memory mapped, so you need to make sure that level 0 has access to these registers. Otherwise you're going to get an exception if you try to configure them. And the other thing to remember is that the memory protection registers are protected under the EINIT scheme, which means that initially to configure them you have to go through an unlock sequence to enable you to configure the unit, and then afterwards you can go through a lock sequence to protect them. Setting up and configuring the memory protection unit initially is very straightforward. You can create a large structure to contain all of the different ranges and all of the different read and write permissions, and then you can have a small piece of software which actually writes these into the various memory locations. As you have a read capability as well, you can read back all of the ranges to verify that you've set the ranges up correctly. The most difficult part of using the memory protection unit is passing control from one level to another level. So for example, if we have a level 0 application and then we want to change the level of the code which is running from, say, a 0 to a 1, then we have to somehow manipulate the 2 bits within the program status word. Now, direct manipulation of these bits can cause some issues. First, of course, is that changing the bits from one particular state to another particular state automatically, as soon as the bits have been written, enables the memory protection unit for that particular range. So for example, if we have the program status words with both the bits being 0, if PL5 is initially set to be a 1, and as soon as we've written a 1 into there, then the code that's currently performing this task has its level change from level 0 through to level 1. Another potential issue is that if we want to go from level 1 to level 3, I have to write a 0 into PL0, and I have to write a 1 into PL1. And the issue there, of course, is that as I write a 0 into PL0, the level changes from 1 back to 0, and then when I write a 1 into PL1, then the range, the protection range actually changes from 0 to 2. So effectively I've gone from 1 back to 0 to level 2. So it may well be that ideally we want to go from level 1 to level 2 without going through level 0. So the issue then arises is how can we change the bits within the program status word without it affecting everything else that's going on in the application. And the way to do this is actually to use a RET-I instruction. And the ret-i instruction is powerful in so much as if you have program status word already on a stack and you do a ret-i instruction, then basically you pop off the PSW word as well as a memory location address. So we could actually transfer both program control and also change the level by careful manipulation of the stack and the values which are on there, and then executing a ret-i instruction. Unfortunately for us, the ret-i is an instruction which is also protected, because if you think about it, your operating system would normally have access to all of the interrupts, and maybe the user application code wouldn't necessarily have access to the interrupt structure. Normally the interrupts are used by the SFRs such as the UARTs. And so what happens if you're in level 1 or level 2 and the memory protection unit is enabled, then what happens is as soon as you execute a ret-i instruction to update the program status words, you will actually get an exception event. And this is because ret-i is not allowed when you're running code at levels 1, 2 or 3. So we have a kind of bit of a conundrum really. It's actually a little bit awkward to actually change from one level to another level. So you have to use careful manipulation of the stack along with manipulations of the program status words to actually change from one level to another. So I've written a series of application notes, of which there are 4 or 5 in total, which basically show different ways of manipulating the information to change from one protection level to another. Not all of the bits are covered under the protection scheme. So for example, we could have memory location FF10 protected under the memory protection level 0, for example. So level 0 could have access to it, but we could deny access to this for levels 1, 2 and 3. But not all of the bits are protected. As you can imagine, executing code would cause all of these flags at the bottom here to change. So really we don't want those covered within the protection scheme, and similarly the ILVL bits, we don't want those covered either. So the bits that are covered are bits 10 and bits 5, and the bits which are excluded are the flag bits. And basically we can read all of the bits from here without there being any issue, but trying to write bit 10 or bit 5 can cause us some problems. Similarly, within the SFR register space, some are included within the protection scheme. So the CPU control registers, for example, the context pointers, the stack pointers. These are protected registers which you wouldn't necessarily want as activity within level 1, level 2 or level 3 to alter. So those are protected, and these will generate a trap event if you attempt to change some of these. Some, however, are excluded, so these are the ones that you'd expect. And the data pointers, for example, so level 1, 2 and 3 code may use indexing and require the data pointers. Similarly, the hardware MAC unit and all the registers associated with that, and also things like PEC transfers, which could be going on that you don't want to be adversely affected. So all the common sense registers, if you like, are excluded from the protection scheme. Okay, so changing the protection level, this is quite difficult to explain how to do. So changing the protection level dynamically is difficult and has to be done at level 0. So writing directly to the PSW bits has an immediate effect on changing the protection level and can cause unwanted effects. Changing the PSW bits should be done in an interrupt service routine where the protection level is forced to 0. In my application example, the PSW bits are managed via a software interrupt, because with a software interrupt, as with all interrupts on the device, the protection level is immediately forced down to 0. If the protection level is forced to 0, then we can change the PSW bits at that level. So by pushing in and popping items from the stack, we can get access to current value of the PSW word, and as soon as I execute a ret-i, then that modified version of the PSW word is popped off the stack and into the PSW register. So what that means is that we can dynamically change the level by careful manipulation of the stack and the PSW that's contained on it. The ret-i instruction at the end of an interrupt routine copies the stacked PSW into the PSW register, thereby updating the protection level. The user must therefore update the stacked version of the program status word to ensure the correct level is set prior to calling a ret-i. Dynamic changes to the MPU protection level should therefore be done in a software interrupt routine using stack manipulation to access the PSW and the call return address. Thank you for watching part 1 of the memory protection unit. In the next section we'll be covering some software examples of how to switch from one software protection level to another.